So today I'm going to be talking about the Presto-Accumulo connector. If you were here last year, I did a talk that kind of introduced it. Just kind of go over a few items of some implementation pieces, design decisions that were not a good idea, and improvements that we made to the connector. I'm not going to cover a lot of Presto or Presto itself. Just do like a quick overview with it. Review the use case that we had that kind of led to the initial creation of it, and then just kind of dive into some items that we had. So first and foremost, Presto itself, it's open source MPP OLAP query engine with pluggable storage models. It was originally built by Facebook as kind of a replacement for the more traditional Hive queries where it wasn't performant enough to have more real-time analytics. So there's a Hive connector for it. There's now an Accumulo connector. There's probably a dozen or 2 dozen or so connectors that you can implement a pluggable storage mechanism, implement their API, and now you can communicate with external databases to fetch data out of it, and then Presto will run whatever query you have. So the Accumulo connector, the aim here that we had was really to accelerate kind of more relational OLTP use cases. In order to get fast query times by abstracting away common Accumulo design patterns like secondary indexes was a big one. You can load data into Presto using SQL insert statements, or there's a Java API that was written to do faster ingestion by skipping the SQL layer. You just write straight to Accumulo. Presto exposes predicate pushdown, so any where clauses in your SQL queries are given to the connector, and it uses these advanced indexes and metrics to kind of determine what rows to fetch out of Accumulo. Most of the queries that we're running range from a few milliseconds to seconds. It really is dependent on how much data you're getting out of Accumulo. The anti-use case is, the millions of rows that you want to run over. This is, unlike the rest of Presto, that's more analytic-based queries and processing millions and billions of rows. This one is not that way. We're talking hundreds and thousands of rows. This was open sourced last year. It was merged into Presto. A lot of the things that I'm going to be talking about today, feature-wise, are in Bloomberg's fork of Presto. So they're also open source. They just haven't been merged back into the Presto mainline just because it takes some time to get everything reviewed and committed there. So the actual workflow, architecture-wise, there's a single coordinator that's responsible for running for planning the queries, scheduling the tasks, things of that nature. And then there's multiple worker nodes that are actually performing the query execution. So when a client submits the query, the connector inside the coordinator looks at any predicates that you have, determines which column to use of that predicate. There's metrics that we're storing a cardinality of certain rows, so we know, say, like how many rows inside this database belong to Adam, if he was the user there. And then the coordinator goes and scans the index to retrieve all the row IDs from Accumulo, and then it packs those row IDs into a Presto split, which is a unit of parallelization inside Presto. And then the workers basically go out to Accumulo, fetch the data from those row IDs in parallel outside of Accumulo, and convert those key value pairs into Presto's kind of internal object model that it uses to actually operate on the rows. And at that point, Accumulo's job is done. Whatever other query that you have, whatever other the pieces of the query plan, Presto goes and shuffles data around as necessary. So if you're joining multiple data sets or grouping by, all of that stuff is done internally by Presto. And one really nice thing about Presto is you can have multiple data sources and have multiple connectors with it. So you can have data in Hive or data in Redis, data in Mongo, data in Accumulo, and write one SQL query against all those different sources. Because again, Presto doesn't really care where it's getting its data from. It just cares more about that internal object model running the query. So this was originally built for Bloomberg. They have this surveillance application where they have compliance officers that are reviewing events. The relevant data points for this talk is essentially username and timestamp for that. So They chose Accumulo mainly for the visibility labels, such that only compliance officers can see certain pieces of data. So we're tagging the rows of data that way. And they have a web application that uses JDBC to execute SQL queries against Presto. The people are, obviously we've worked with Accumulo APIs. For people that aren't familiar with Accumulo or Java, they can be a little cumbersome with that. And most web applications, they're very familiar with JDBC, very familiar with SQL. So we kind of went through this effort of implementing a Presto connector to Accumulo in order to get fast query times, while also being kind of user-friendly in front of that. Ingestion's done through Storm. They're using this Presto batch writer that was written that it takes in the same mutation object, but it handles indexing the data as well as creating metrics and writing them out to multiple databases or multiple tables inside Accumulo. All their queries from a compliance officer, they're querying, what are the last events from the last hour, so it very heavily relies on the event time index to get these recent events. So we're indexing a bunch of different columns, but it turns out that the event time is pretty much the only important one for the actual major use case. But for ad hoc queries, we'll leverage the other indexes. Query performance, 10 milliseconds to about 10 seconds, depending again on how much data is being processed. Table sizes in terabytes on thousands of tablets, and we're deploying Presto and Accumulo on Mesos on bare metal. Check my time, 1:38. Okay. So now to get into just kind of the lessons learned that we had. There's no trivial way with the APIs to age off or update any data. So we went to start, one, just aging off data. We keep these metrics, which are using the sum combiners, so the timestamps are constantly updated. So once we delete data, if we use the age-off iterator, those metrics are no longer going to be accurate, and we heavily rely on them in order to choose the optimal columns to fetch the indexes from. Additionally, delete mutations were completely ignored by the Presto batch writer. And in order to update any data or delete data, you had to go and use Accumulo APIs to kind of work with the tables to manually edit indexes and increment or decrement metrics. So kind of the next big thing with this was just improving the API so that it's easier to use for end users. Now, any delete entries or any delete column updates, Presto will actually detect those, and it will go and query the row of data and figure out what rows we need to drop from the index, what metrics we need to decrement there. So there's explicit API calls to update rows of data and delete rows of data. The next step of this, Presto has a delete SQL statement, would be actually integrating that API with the delete, so you can actually use SQL to drop data. So kind of the lesson learned here was just we needed a clean API to delete stuff, and we're still working on it so that you can use SQL and automatically drop data, since we aren't able to actually use age-off iterators. Next was kind of more with resource scheduling and using resources properly. We had this arbitrary row batching where the connector would get 50,000 row IDs that it's going to scan out of Accumulo, and it would pack 50,000 rows into a single split and then send it off to the cluster to be processed. So if you have 10,000 row IDs that are going to be scanned out of Accumulo, you'd get 2 splits. And the split is that unit of parallelism again. So you'd either have a variable number of splits all the time, you either create too few splits. So if you only have 2 splits, each Presto worker can run 80 tasks by default. And if you have 10 Presto workers, you're not really fully leveraging the parallelism inside Presto. Additionally, it caused problems with concurrent queries over very large data sets, which we shouldn't have been doing in the first place, where you'll run over millions of rows, and it would basically block any smaller queries that are running a lot of fewer rows because it would fill up all of the task slots on Presto. And also 50,000, like most numbers in configuration, there was no research done at all about why that number should be chosen. It just seemed like a good idea at the time. So we ended up basically just creating a simple formula to kind of determine the number of splits per batch. When we were looking at SLAs of how many concurrent queries do we want to run, we ended up with, we want to be able to run 10 queries concurrently inside this Presto system. So what we would do is look at the number of rows that we're going to scan from those metrics that we're storing, divide it by however many splits per worker that you can configure. So if you want 8 splits per worker, you have 10 workers, we can figure out how many row IDs we actually want to put in a single split. So this led to better resource handling, better scheduling inside our system, better concurrency overall. And you can kind of tune this to fit your use case appropriately. Next, we're looking at index retrievals. So the connector would regularly spend several seconds fetching row IDs from an index. The process that it would do it, so here you have a query, or a little Venn diagram, where on the left we have all the row IDs where the user is Adam. So if you're running a SQL query that says, give me the row IDs where user is Adam and the date is today. What it would do is it would scan all of the row IDs where the user is Adam. So you can think every single time Adam has ever sent a message, we're tracking that row ID inside Accumulo. So I've sent a lot of messages over the past years, so all of those row IDs are stored inside the index. Additionally, there's all the row IDs where the date was today. So every single message that all of us have ever sent, there's an index entry that we're tracking. And in order to satisfy the predicate, they're kind of in the middle there. They overlap. So if you think of the millions of messages that are sent every day, that has to scan millions of rows out of Accumulo, and then scan millions of rows where Adam has sent a message, more like thousands. And then it does set intersection in the connector to determine which rows it's actually going to use and send to the workers for processing. So it wasn't distributed. It was single-threaded process. Get all the rows for Adam, get all the rows for the day, set intersection. So it's regularly pulling out more rows than necessary. This was kind of the biggest optimization that we had, where it was taking queries that were taking 40 or 50 seconds down to a handful of seconds by adding these kind of new features and optimizations. First, the easiest one was just add a thread pool to fetch the row IDs in parallel. That was simple enough to do. The second one was we added composite indexes. So now we're storing additional data where we're taking the username and the timestamp, creating a separate index column of that and storing it in Accumulo. So now we're just kind of pushing that set intersection to the tablet servers and just kind of storing more data, but out of that we get faster queries. And the third one, which is the biggest one, was distributing the index lookup to the actual worker nodes. So when you would get a query over an index column, and I'm referring to both like the regular single column indexes and composite indexes, what it does is it will split the range into however many splits it ends up coming out to. So if you have a query, say from a range of Alice to Wendy, what it actually does is it'll convert that into 3 equidistant ranges of Alice to Aaron, Aaron to Olivia, and Olivia to Wendy. And then each one of those ranges gets sent to a worker, and the worker is then responsible for scanning that range out of the index table. And then it uses those row IDs right back and scans it. So we added more parallelism here. We added more indexes to make these queries faster. It also was a lot better resource-wise, where for those queries I was talking about that had millions of rows, it would regularly blow up the heap of the coordinator because it would pull 40, 50 million row IDs into the coordinator, and then it would crash, and the system is no longer available. So by distributing the index lookup, it's just being nicer to the JVM. Next up, that was a big issue, was that we had no query history. So the coordinator tracks recent queries that have executed through their UI that they have. You can go in, take a look at it, see what's running, see what ran. But that would get age off. I forget the default, but it's usually a few hours or a day or so. So we had, just no history there. So Presto released this event listener API where you can go and implement an event listener that every time you submit a query, every time a split is finished, and every time a query is finished, it gives tons of metrics about it. What was the actual SQL query? What session properties were used? What table was it run? What output table? Who ran it? When it ran? All these different metrics about it. So we thought that this would kind of be a good way in order to track this history. So we added an Accumulo event listener, which essentially takes all of that metadata from the event listener hook and writes it to a Presto-Accumulo table. And this is great because all this history is now stored in Accumulo. So we're persisting it between any restarts of the coordinator. We can keep as much of it as we want, and we can also query it through SQL. So we can generate usage reports. We can determine SLAs of individual queries that users are running in order to kind of detect when we need to scale Presto if we need to. Next in the use case, it changed a little bit in that you weren't able to actually see the full visibility label or the timestamp on the entry in Accumulo through the SQL API. So what they were doing is having to basically scan Accumulo through the regular Java APIs in order to access that information. And we didn't want to kind of add it to the DDL where you have to explicitly sign it or explicitly define everything, because it's weird from a SQL perspective because SQL doesn't really have visibility labels or timestamps. You have to add them manually. And it just mucks up your DDL where if you have 100 columns, you now need to go and define a visibility column and a timestamp column for everything. But what they do have in Presto is you can tag a column as hidden. So what we did was add these hidden visibility and timestamp columns. So you don't have to define them explicitly. You get them free for all these non-row ID columns, and you can just select them directly. So for every single column name, you just tack on _vis for viz and _ts, and you're able to now pull that information out through the SQL API. So we had to expose this there. The downside of it that we're seeing now is there's no way to write visibility and timestamp information through SQL, so we kind of have to deal with that. In that, Presto literally filters out all hidden columns when you try to do an insert. So if you said insert username _viz and username _ts, it will just reject it and say, I don't know what this column is. So it makes it difficult to insert data through SQL if you actually need visibility and timestamp information, which it's Accumulo. You generally need visibility information for most use cases. I don't really know if we're going to get around that. We'll just use the Java APIs to ingest data. The next thing, which is still a big problem today, is these large ad hoc queries. So most of the use case is done through that web application that's running and fetching hundreds, thousands of rows at a time, small amounts of data. But there's this one use case where they want to look at days or weeks of data, which is millions of rows inside the table. So when you run a query, it'll run it like any other query. But what it does is it essentially saturates Accumulo and takes up all of the scan threads and backs up all the scans on the tablet servers, which blocks any other query that's trying to run. And then people complain that their SLAs aren't being hit. We're still not really solving it today. I didn't want to add any code that will reject a SQL query, but I ended up doing it. So by default, it's 50 million rows. If the connector is going to scan 50 million rows, it just throws an error and says, I'm not going to do it. We've been brainstorming ideas for it, such as reading the R files directly out would be better and just skipping the tablet server layer. right now, we're just having this particular use case move to using Hive and querying it through Spark or Presto to actually access the data. But it would be great to not have this type of restriction in Presto. You should be able to read as much data as you want out of Accumulo, but we don't want to block the system. So the big lesson learned here is don't use it for your analytic queries. It's not meant for that. Either duplicate your data, or maybe someday there'll be cleaner APIs to read data out of the R files on an online Accumulo table, as well as getting the data out of the mem table. Next is what I'm working on now. That's almost done, hopefully, is this index hotspotting. So when this was built, we wanted to kind of get it out the door as quickly as we could. So we had a basic reverse index for all these columns. We're taking the value of the cell on the table, making it the key, or the row ID rather, and the row ID for the actual row is getting stored as the column qualifier, and we stick it in a table, which causes all the problems that you want to avoid when you're doing indexing in Accumulo. Particularly, we had low cardinality columns, was causing extremely wide rows, regularly spitting out errors, and we'd have to go and drop those indexes. Some stuff was just not good on ingest, like we're indexing question marks, for example. Not really useful at all. Additionally, all of the timestamp columns are monotonic increasing indexes, which you're not supposed to do. So we had hotspotting, and still do have hotspotting when we're ingesting data into the table. The actual key distribution is all over the place because we have multiple different data types that are all going into the same exact table inside Accumulo, as well as a separate table for metrics. So we're kind of duplicating the problem in that there's two tables that now have hotspots for all these index columns. Additionally, it's extremely difficult to delete a column. So if you have an index column and we want to drop data, we're not actually using this index column, I don't want to use it anymore, we'd have to configure regex filters on it to delete data from that column and compact and merge the tables. We recently did this about a month ago on our production systems to drop terabytes of data in order just to reduce the cluster size. It took like 3 weeks to compact all of the tables and merge all the tablets across the 4 Presto tables that we have, which is 12 Accumulo tables. It was just a big problem with it, so we kind of wanted to address all of these issues with our indexes. First and foremost, this is a very large refactoring effort that requires migration from the old tables to the new tables, which we're still figuring out how to do. We want to do to kind of address the key space issues as well as the blanking. Yeah, and get rid of the regex filters. Addressing the key space, get rid of that so we can drop columns really easily, was we split the index table into one table per index column. So when you create a table inside Presto, it goes and will automatically create all of these index tables that are named after the index columns inside of it. We also took all the metrics and put them in the index table. They're in a separate locality group from the indexes, but whereas before the metrics were kind of an afterthought of indexing, they're all in the same table. And additionally, we went through and are adding these index storage methods, kind of API that you can encode or decode the data. So there's one that just shards it, so it'll just hash the value and stick a number in front of it in order to kind of address actual hotspotting problems. And another one that will just postfix random data to the end of a row. So that addresses the monotonic increasing bits, where now we're distributing it across multiple buckets inside Accumulo, as well as the high cardinality pieces, where you can now just have junk at the end of it to get those tablets to split when they grow. There's kind of smart defaults for this, like timestamp columns, dates, things like that. it'll automatically use these storage methods. For other things, you actually have to declare it explicitly. When you say username is an index column, I want you to use the postfix strategy with 8 bytes at the end or something like that. Those are the only 2 right now. I don't know if there's other ones. I'm open to kind of suggestions to kind of see what indexing strategies there are to make be a little bit nicer to Accumulo from a Presto perspective. So we want to support these multiple index strategies. We're working on, I have a Spark job that copies data from one table to the other that I need to finish before we can actually start testing it, but we're hoping that this will just kind of mitigate a lot of the issues that we've been seeing with the first round of indexes. Just to kind of summarize all these things that we've done, we added deletions to the Presto batch writer. Next, we're going to add it to the actual SQL statements. We had smarter resource allocation for how we're executing queries and how many splits we're generating. Adding composite indexes certainly helps answer a lot of the types of queries that we had. And that supports any number of columns that you want. So it's not just 2. You can do 3 or 4 or however many, depending on types of queries. There's a query archive, and a corollary to that was we added support for the row data type inside of Presto. We've distributed the index lookup to all the workers to kind of help reduce the memory footprint on the coordinator, as well as just have faster queries by parallelizing the index lookup. There's hidden visibility in timestamp columns, so you can now select that out of Presto with SQL. If you are scanning too much data, we'll throw an error in your face and say, don't do that. And we're also working on these hotspotting index stuff. The index hotspotting is currently in a branch on, again, the Bloomberg GitHub. I'd encourage you all to take a look at it, if you think. It's certainly helped where you look at a use case. Like, the goal of it is, I can just start using this. It's a SQL-like use case, but I don't want to use a SQL data store. And now, any questions? Either about this or the Presto connector itself, if you all have anything. No? All right. Thank you, guys.